Hello everyone. I hope everybody's doing fine today. Probably not as bad as me.
Why do you keep saying that?
Oh, I hope they're doing better than me. That's kind of like that, by default, right?
Yeah, that's true.
That's my son on the other side.
Hi everyone.
And this week we're doing standard model of quantum mechanics, okay? And we started the week with what? With the gluons, then we went with quarks. And yesterday we found out that it just doesn't stop there. There's more to it. There's all these weird particles out there that they've invented or found or discovered. I'm not sure if you can call it discovered. It's just that they're seeing properties and emergent properties where out of a system something develops and they just give them names. That's what these people do. They look at these squiggly lines that come out of, the collision, or so they think, collision of particles. And they see these squiggly lines. They say, oh, that one's got so much mass, so much speed. We needed so much energy to accelerate it to get that squiggly line. And so they they kind of categorize, and they have this album of photographs of particles. It's a collection, of particles, and that's what they do, and they give them names, and that's what they get paid those big bucks for. Okay, so what is a standard model? Well, the standard model looks something like this. Okay, let's briefly go over that. And there's 17 particles in the standard model.
17 particle categorizations.
Well, yeah, and again, let's make sure these are just the primary ones, okay? Because it doesn't stop here, obviously. In fact, as you can see, there's a glaring absence there, which is the graviton. And because they continue to claim that it's a hypothetical particle, meaning that all these have been proven. You've got no say in it anymore, okay? But anyways, you got 6 quarks, okay? Those are the upper 6 violet on the upper left-hand corner. You've got the 6 leptons, which are the lower green ones, 6 lower green ones. And then you have the gauge bosons, including the Higgs boson, which is a scalar boson. And those are on the right-hand side. So that's how we start, okay? Those are the particles that form the the matrix, the little standard model. But it doesn't stop there. We've got some others, and like we went over yesterday, we have some exotic particles. Here we have them. We have the onium, the positronium, muon. I can't even pronounce it. Muonium. Oh man! And they form part of what is called an exotic atom. Then we have the true muonium, or the muonomium. Muononium. I got it right the second time, I think. Pionium and a protonium. Okay, so we have all these weird particles that form exotic atoms. Okay, now what does this really mean? It means that these people are saying that, if you went to high school, you learned that an atom is made of a proton and an electron. These people are replacing the electron. They're taking the electron out. Now they're putting in there a muon, which is heavier, more massive than an electron. And so you have an atom, listen to this, we have an atom that's got a proton, and it's got a muon going around it. No longer do we have the standard, petty kindergarten stuff that you learn in high school, of the electron going around the atom. Now you have a muon going around it, or maybe a pion.
Isn't it just a differently named orb? It's the same thing, just with a different name.
Different.
It's not an electron now; it's just a muon.
No. They're saying that the particle is being replaced
By some other
particle. It's a different particle out there that they noticed somewhere, and they're saying that, oh, this atom seems to weigh a little more because now the weight has changed. Remember, the muon weighs more, is more massive. than the electron. If you replace the electron with a muon, now you have a different kind of atom. You have a different, and you know, they say, well, these atoms exist, but you do have a different atom.
Okay, but what's the muon if not just another ball? You trade in the electron bead for the muon bead.
Well, think about that for a second. Shouldn't that change the properties of the atom? I mean, you would think that it's not the same thing to have a muon than to have an electron going around I don't know, a proton.
If the new thing is different anyway, like if it's lighter or smaller.
Well, this one is heavier.
The muon is heavier?
Yeah, the muon, the pion are all heavier than the electron is one of the least massive ones in the system.
If you change the air, the helium in an air balloon, and switch it in for, I don't know, radon gas.
Or hydrogen, for that matter,
or they trade it in for xenon gas or something.
Yeah.
That thing won't float, so because it's heavier.
Because it's got different properties. And that's my point. My point is that now imagine two atoms, right? And they're going to form a chemical bond of some kind, of covalent bond. But one of them, instead of having the electron, suddenly has this weird, it has a muon. Oh, I mean, doesn't that do anything to the?
It's got to be different.
You would think.
What
Maybe no. And think of this: a muon has mass, therefore it doesn't travel as fast as light, because only massless things, they say, travel as fast as light. Neutrino is suspected of being one of those because, again, these are the so-called massless particles that interact poorly with matter. That's how they say this. And so if you replace this now with a muon, this electron with a muon, it's got a different weight, a different mass. You would think that it travels at a different speed. Mm-hmm. And now you're going to put two atoms together. One's got an electron and expects to see an electron on the other side. Suddenly it sees this Neanderthal there, What's that guy doing there? A muon. Or a pion, for that matter. It's got the atom has to work differently.
Well, what do they say?
Well, that it does. Well, I don't know. I mean, I don't even know how they detect these things. I mean,
yeah, surely the atom with the muon is different somehow, or else they wouldn't give it a different name.
But then, how is it that they came up with all these exotic atoms?
But they're all or many of them are theoretical or hypothetical.
I'm not sure they're. I mean, these people are.
And a lot of those is said is a hypothetical particle because they see, okay, if we have an. I need the list again, but
which one of the
particles?
Oh, here I was going to cover that next. So here are the quasi-particles or quasi-particles, quasimodo, or quasi. Well, yeah, quasi or quasi.
They're basically. Let's take the Bogoliubon. Right?
Which one is that? The
second one.
Number 2. Okay, we have a broken Cooper pair.
So,
okay,
I don't know what a Cooper pair is.
Well, it's got an electron. You can see the underlying particle is the electron.
Okay, but we have a Cooper pair, right?
Okay, we have a Cooper pair.
Someone says, okay, but what if that Cooper pair is broken? So then it's a hypothetical. If we have a Cooper pair, whatever that is, and it's broken, then we call it a Bogoliubon. With any of these,
you can use any of them for that matter.
Bipolaron, right?
Yeah, the bipolaron.
You have
easier to say.
You have two polarons. Let's say you have a polaron. Then they're like, wait, what if you have another polaron and they're bound? Oh, we got to give that a name. What if we have 3 polarons and they're all combined? Oh, we'll give that a tripolaron.
Yeah, in this case, I'm not sure.
They're all hypothetical in the sense that they're just kind of playing like mind games. They're just kind of like the chart. Just saying, okay, what are all the ways that we can even imagine, or not even imagine, that's the wrong word. What are all the feasible combinations of properties? What are all the combinations of properties you can come up with? If you have 1,000 combinations out of all the properties we know of atoms, if we have 1,000 possible combinations of all the properties that we know of, then we're gonna have 1,000 names of 1,000 different particles, basically.
Yeah, and I guess what you've done with this is just created a job security. You've got all these particles running just forever,
Yeah, but
and you're
they
breaking
don't do
them
it for job security. That's
No,
not
no,
what they do.
I'm sure they don't, but I mean that's the effect.
Yeah,
that's
the
that's
effect,
how it
but
ends up being.
I think they're just
always.
trying to get everything down so that they can have a name for everything. What are all the feasible combinations of properties? And for each of those combinations, we're going to give it a something on. So that we have it all categorized, we know exactly what everything is named.
But just imagine for a second that that the rope model comes in there and says, there are such things as discrete particles in the universe. Yeah. And suddenly all this gets washed away. This complexity is replaced by this absolute simplicity of the rope.
Well, it's not simple. It's simple in comparison.
Well, yeah, okay, but it's much more simple. No, but I mean, in this sense, it's simple. You can say it's simple. If the entire universe is comprised of two atoms and united by a rope, and that's all there is, no matter where you look in the universe, it's just atoms connected by ropes. Mm-hmm. Compare that against the gazillions, these 200 particles. We need this one, Peter for this one. We need Johnny for that one. We need Joey for that one. We need Tommy for the other one. We've got all these different particles named, and what are they? Well, they're not even particles. They're some kind of vibration of sorts, and it's got so many properties. This one has charge, and this one has flavor, and this one has, they've got all these different categories. It's so complex, but now suddenly you bring this and say, look, guys, let me make it simple for you. Let's bring William of Ockham in here and make it simple. All these guys, they lose their jobs. There is nothing for them to do, and we turn CERN into a white elephant.
Well, I mean, that's kind of the point of science is...
to turn them into a white elephant?
To end science at some point.
No.
That's the whole point of science, is to end it.
No, they claim it's not. They claim science is about discovering, right? In other words, it's about seeking, not about finding. And this is an endless job security, at least from that point of view. But then it turns out that, they claim that you never find, you always seek.
Isn't that just a presumption?
Well, that's their philosophy. It's their philosophy. It's what's in their minds that we never get to the end of the road.
But it's kind of like an explorer who thinks the Earth is infinite.
Yeah, and he's going around in circles.
Yeah, you already found everything. It's possible to find everything.
He's going around in circles.
Once you've found all the continents, you're done.
Yeah.
These guys are like, no, there's always another continent to be found. The seeking is the important. Like, no.
Well, that's a good analogy, but see, keep it under this focus now. Okay, so we found every continent on Earth. Now we've graduated. Now we're going out into outer space, and we're going to be looking for planets and moons out there.
Yeah, but for this, it would be as if every planet were like Earth.
No, but that means that there are other continents.
No, the same thing as a carbon atom up there.
What I'm saying is, you're going to another planet. There are going to be continents over there. It's in other words, the jungle doesn't end at the edge of the Earth. You can continue all the way to Mars and to other stars where we can find planets and whatever. So this is more like that. It's like it's an infinite universe and it's an infinite science. There's always something to be discovered. But that's the philosophy. That's all I'm saying.
But what interests me about the rope model, if it became more known, if it became spread enough that it starts spreading itself, that kind of level of fame, where people can actually see it and kind of mull it over, because right now it's not known enough for people to even mull it over. 99.9999999% of people
don't even know about this stuff.
Yeah, everyone but us, basically. Everyone listening doesn't know about this theory or has never heard of it, has never even had time to think about it, or even a chance. But if enough people have the chance to think about it and kind of give it a chance and be like, oh man, this actually makes more sense than what we've been hearing.
You got to contrast it for them to see that.
Yeah, you kind of say, oh, this one makes more sense, and it's kind of like how people change religions or adopt religion or drop a religion. you know, the rational people who do that, they kind of like do it in private. They don't do like some big spectacle. Oh, I'm a whatever now.
Yeah,
you know, the people who are you know cool.
Yeah.
They just kind of go, oh, I like this one more. I'm just gonna kind of go my own way. Like, okay, you guys can keep your mathematical physics, but I kind of like this rope model more. And the more and more people that kind of do it under the rug, kind of like that, where people adopt this new, simpler theory or explanation of how the universe works.
But because these are all descriptions. Yeah. Keep in mind these are all descriptions.
We don't even have an explanation.
We don't even have an explanation.
But I'm kind of excited for people, just kind of, you know, people that we'll never meet, people that we'll never see, just kind of in their living room, just kind of going, huh. That's all I like.
That's already a victory, right?
That's a victory. Like I won't be able to see it. You know, I won't be able to see that victory. Yeah. It's just someone going, huh.
Yeah.
I like that, you know?
Yeah, it's like different.
Instead Not different, it just makes sense.
Well, that's one, but it's different in the sense that all this stuff is quite boring, you know? I mean, what are these guys doing?
It's
just naming things?
What?
I mean, look at these names for the quasars, and I'll just give you part 2 here, which is this one here, which is starting with the P's. We have the phason, the phoneton, or the phonon, the plasmaron, the plasmon.
But I think they're also getting bored with it. That when you say it's boring, that's what they were talking about.
Well, they're just creating new names.
When they were saying physics is dead, because it's like, okay, we had our fun, but now it's kind of like the same thing. Okay, yeah. Now we're just putting on.
Yeah, but what these people do is equations to characterize the behavior of what they observed in the lab. They see a squiggly, some vibration. They say, "Oh, this is a new vibration. I've never seen this before. I'll call it Johnny." And my name is Johnny.
No, it's a Johnny on.
Johnny on.
But you can tell that everyone's kind of getting bored with it. It's like, okay, we haven't explained anything, but we don't have anything better. See, that's the thing you keep missing. Because you do have something better, so you don't see it from the normal person's point of view.
Is that what it is?
Everyone has nothing better. That's all we got.
Maybe that's what it is.
That's literally it. I mean, you have the punchline in your head. You're laughing at everyone like, they don't even know. Oh, great. But, share the joke, you know. You're the only guy laughing here because you're the only guy that understands the joke. No one has anything better, and that plays the biggest role. Because in the Middle Ages, we had religion. No one had anything better. So that's what was dominant. No one could come up and challenge, religion, and the few that did.
Yeah, but when they came across a different religion, like a Christian encountering a Hindu or a Buddhist or whatever, it was like shock, or a Muslim, it was shocking because suddenly what do you mean you don't believe in God?
Why? Because there's
I'm
so
one
much
with the universe.
Since if no one has anything better, right? This is the best we got. This is the best humanity has from everything that I know. And then you see someone with something else, it's like, what have I been thinking 20 years? You must be wrong. There's too much investment in whatever you've been holding on to.
Yeah, but keep in mind, a lot of people change, not a lot. In fact, that's the opposite of what I want to say. Very few people really change religion. They're so indoctrinated, for example, with Christianity, that you won't find too many Christians that really hop the fence and become Buddhists. You'll find them, but not you don't find a whole population.
My point is, it goes beyond religion. Even most people, 90% of people, don't change their mind about anything.
Do you think the internet's going to change that? The fact that can that convince many people at the same time? I mean, the priest, he only preached to his congregation, but now you have priests that preach to millions of people.
That's how it's.
We're
in the perfect time to.
On the one hand,
the perfect time would have been 1900s when all this was starting. If you threw the rope model, then it would have been on.
Yeah, but now you got a different situation also. In that you can influence many people at the same time, right? But what's the problem? The problem is that you get crowded out by the billions of people on the internet.
Oh, the
that's
advantage.
That's a disadvantage.
The advantage that the rope model has in science in general over diet,
over
diet, like videos or information about what to eat or how to live, is these are all kind of subjective. While the great thing about science, at least the way you do it, it's self-explanatory. You don't have to take anyone's word for it.
Because of the pictures, you mean?
it's self-explanatory.
Well, today I put an article on.
But what I'm saying is, whoever picks up the rope hypothesis doesn't have to take it on authority. It's just that's the biggest thing. With diet, you don't know who to believe, who's doing the right studies, who's doing what. There's a lot of lies. There's a lot of misinformation. Here, there's no misinformation.
Here today, I put an article on that.
It can't be misinterpreted. I mean, it can be misinterpreted, but I guess not if you do the video. We need the video.
Today, I put an article on what is it? On magnetism, how two magnets attract. So here we have two magnets. I love that clicking sound. It just, get your fingers out of the way because it'll, get you. And, here's a simple system. This is two pieces of metal. That's all it is, And
that's all we see.
Yeah, but the point here is that it should be a quick explanation. We just need to figure out what's between these two magnets, right? That's pulling them together. Or outside, like some people think that they're being pushed from the outside. Fine. You can even feel, here you can see them pull, they're pulling, but these people are saying that something is pushing my hands, which is pushing the magnets together. This is how these people are retarded, that they can't even figure out something as simple as that the two magnets are being pulled together, not pushed together. But today I put that in in a little article, and a lot of people are reading it. I had like 200 hits in the first minute. I'm not kidding you. It was whoom. Suddenly a lot of
nothing.
No, I know. But
by normal people, by normal YouTube standards,
it's not viral in that sense. It's not in the millions. But not too many people deal with science and technology, anyway. But the point here is that all they had to do really today was look at the pictures. And there was like I said, if a picture's worth 1,000 words, a video's worth 1,000,000 words. And this was a video that was worth 1,000,000 words. You just look at the little cartoon there. It's 2 minutes, 3 minutes total. And you don't have to take my word for it. You can understand the mechanism. And that's what I said. Don't believe me. Understand me. But just look at it, see if you understand the mechanism, what causes it, what I'm proposing causes it, and then you reach your own conclusion. So you don't have to rely on my authority or anybody else's authority.
That goes back to what we talked about like 2 weeks ago when we were saying how true science is self-explanatory. If you have a video of how something behaves, you need no words, it's universal language. Every single person who has any basic knowledge of life, of just being alive for
can relate to
maybe 5 years. I mean, babies, kindergartners can learn this. They just see the if you see a domino effect, you know why the 45th domino fell over. It's just that needs no explanation, needs no introduction.
Right.
You don't need Chinese subtitles.
And that's why I'm saying physics is done with objects. If you can see objects performing their thing, it's self-explanatory. It's only when you have to introduce concepts and you say, well, the force came in, we have a field, we have energy, and people don't understand what those things are because these are concepts. And when you ask the question, well, what is a field? What is mass? You got to go to college to learn that.
Well, what did you want to talk about the wave function?
We're getting there, but this is the issue. The issue is that physics is done with objects, and once you put objects on the screen, it's self-explanatory, and in that sense, you're right. But see, the problem there, the counter argument to that brought by the mathematicians is that science doesn't explain. Science describes.
Well, I don't care what they call it. Well, everyone knows what we mean by science. When someone asks, "How do two magnets work?"
But they don't even ask the question.
Everyone. There's a lot of people
the mathematicians don't. They say,
"Well,
there's so many Gauss."
I'm talking about normal people. Normal person who wants to know how does magnetism work. He wants an explanation.
Right.
That's a scientific. Everyone understands that's a scientific question. I don't care how you define science.
Yeah.
You're wrong if you don't define it.
But then they tell you positive attracts negative, and I have just explained it.
Yeah, but that's not.
And see, you wanted an explanation. There it is. Positive attracts negative, and and that's That's how they get around. Anyways, then we have, before we get to the wave function itself, we got to go through this spin thing. And real quick, spin is an intrinsic form of angular momentum. Okay, we covered that yesterday, right? And you say, well, what does that really mean? And so I'm going to put it in pictures today. And here is the first part of that picture. This is the classical spin. This is what we understand about spin when you spin a top. Okay, so let's look at the parameters that we look at when we look at a top. Okay, and it goes something like this. Let's see. Let me get this in there. It says, let's start at the beginning here. Wait till it gets to the beginning.
Is that a watermelon?
Something like that. Well, it just says essentially that that you know certain things. In classical physics, the spin of an object can be described by an arrow. Okay, the length of the arrow indicates the rate at which the object is spinning. An arrow pointing in the opposite direction indicates the object spinning in the opposite direction. Okay, fine, it's straightforward. If we change the axis of rotation, the arrow changes accordingly. And finally, at any given moment in time, this arrow can be thought of as the combination of 3 arrows pointed in each of the 3 dimensions.
It can also rotate in 2 directions, clockwise and counterclockwise.
Yeah. Well, I guess you can make it go north, south, east, west.
Yeah, but then you're changing the
just you're changing the observer's perspective.
No, you're changing the direction of the vector.
Yeah,
That's
of course.
different. But I'm saying with the same vector.
I see. Okay. You're right.
Clockwise.
Yeah. Okay. In that sense, you're right. And then okay, so that's spin according to a classical, what they call classical, which you can say is rational physics. Now let's go to irrationality here, and here we have the comparison. This is the comparison of classical versus quantum. Okay, it says, let's wait till it begins. Gets this art. Give it one more second here. It says in quantum we never measure 0 for the components of the electron spin. Okay, it says it's therefore not possible to accurately represent spin in quantum. Okay. Classical physics is possible. Oh, I didn't get it. Just goes so fast. In classical physics, these arrows can have any length. Okay. In the spin particle is aligned in the z direction. Then in classical physics, the x and y component spin would be measured to be 0. But in quantum mechanics, we never measure 0 for the components of the electron spin, or the x, y, z directions. It is therefore not possible to accurately represent spin in quantum mechanics with arrows pointing along an axis of rotation. So we have.
What did all of that mean?
Well, it means that they don't know. That's essentially, they can't measure the spin of a particle in the same way that you measure the spin of a top.
Because it isn't always along the same axis?
No, remember, this is all mathematical stuff, okay? Yeah. So that's the first thing we have to keep in mind. They're trying to mathematize it. They're trying to put an equation to describe this thing. And what they're saying essentially is that if in classical mechanics and regular mechanics, you know the speed of a top, and you know in which direction it is pointing, and that gives you information about the other 2 axes. You know, like if the top is pointing upwards, north, in the z-axis direction, you know that it's spinning in the xy direction, right? All that information is lost in quantum mechanics, because once you try to measure, you affect this. It's like touching the top and saying, oh, let's see what direction it's moving. You touch the top and the top stops spinning. And so now you lost the information. And that's what the people are saying. You can never find, you can never figure out what you're measuring, because as soon as you try to touch it, as soon as you try to measure it, you affect a system at the quantum level. Okay? So we're talking about little particles that you can't even see, and you're trying to measure that particle, and you're saying, let's see, what is the spin of this particle? In other words, if I know the z-axis, what is the y and the x-axis doing? You can't do that in particle. You can do that with a top, you can't do that with particles. That's what they're saying.
how do they know that they're changing the result by looking at it?
That's kind of like a long story. It's got to do with the uncertainty principle, enunciated by Heisenberg, Werner Heisenberg, and essentially he says, when you try to look at a system, you're throwing a photon at it. And a photon, as we know at least from the photoelectric effect, is affecting that particle, the particle you're trying to look.
Yeah, but that's dumb, isn't it? The photon is coming from the object. We're not throwing a photon at it when we look at it.
Well, the photon goes both ways. No, but in order to see it, you have to bounce a photon or an electron.
But it's
because
already
they do it
bouncing off of it.
No, hold it. Let's get it right.
Yeah.
A SEM, scanning electron microscope, or a force, atomic force microscope. They have this power to see very small things. But in order to see that thing, you got to shoot an electron at it so it bounces back to your eye, or hits it and throws a photon to your eye.
That's
so
how the machine works.
Yeah, but that's how you get it. But that's how you get it into your eye.
Yeah, but
because you
isn't
can't
it
see.
Already?
No, you can't see it at that level. In order to see it, you need to bounce something off of it. That's what they're saying. You can't just see it directly, like, oh, I'm going to wait for a photon from that
then
little.
What they're saying is it's not shooting photons.
It's shooting
It's
photons, but
light.
it's shooting photons, but at a frequency or a wavelength that we can't see.
So you have to stimulate it with your own photon.
It's kind of like that. Like, you got to give it a shock to see what does this look like. And when you give it a shock, you say you disturb the system. And so it's like throwing rocks at something that you want to see. You're using the rocks to see. And you throw rocks at it and you say, why can't I see it? Or, well, because you threw a rock at it, at the dog. So the dog's no longer there. It went away. Okay, so you can see some of these things here. Here's another part of spin. For example, the arrow representing the z component of an electron spin is always observed as either being pointed up or pointed down, but the length of this arrow never changes. So the length, it tells you the magnitude.
How much?
This does not accurately describe an electron's quantum spin, as this picture falsely shows. In other words, they're saying, you don't have a full description of the electron, but because if you get information on one thing, you can't get it on the other. That's what they're saying. And so you can't get all these parameters simultaneously. Okay.
If you get the X, you can't get the Y. If you get the Z, you can't get the X.
And that's essentially what they're saying. And so it's not humanly possible within quantum mechanics to get all the information that you want from one of these systems.
Assuming you did, what does it matter? Assuming you knew the exact magnitude, X, Y, Z, everything of a particle.
They need it for the equations. They need to put all these values. See, it's got to do with Schrodinger's equation. We're going to get to that in a second. But essentially, because that's got to do with a wave function. And we're getting into that in just almost there. But the point here is that they want to put some of these values. See, they look at the wave function. The wave function has all these little parameters in there. You got to put numbers in there for these variables in order to know where it's at, how fast it's going, what's its mass, that kind of thing, how much energy you need. They need all this information to put in the equation. And the problem is that, they want to get this empirically. They want to go to the lab and say, okay, what is the speed of this particle? Let's put it in here. What is the orientation? Which way is it pointing or whatever? They want to put that in there. And the issue is that when they go to the lab, they can't get all the information at the same time for a given particle. If they get one piece of the information, they don't get the other, and so they can't put these values in the equation. And so they're out of luck. Mother Nature doesn't allow them to do this, according to them, for quantum mechanics, okay? And, okay, so just to finish up on spin here, you can't get if we know the electron spin in one direction, then the electron spin in the other two directions are inherently unknown. Suppose we measure an electron's component of spin in the z direction. If the only other measurement we make on this electron are other measurements of the spin in the z direction, then we will always obtain whatever it was. I didn't get to read it. The moment we measure electrons' component spin in one direction, we lose all knowledge of the other two directions. In other words, you can't get all the information on a given system at the same time. Okay, you get one piece of the information, you don't get the other. Essentially, they're saying that. And okay, and the last one here. Let's go to the uncertainty, and it says, but if the system consists of just this one electron and nothing else, there will always be exactly one direction in which it's possible to know the spin with certainty. But it says the more certain we are about the spin of an electron in one of the three dimensions, the less certain we are about its spin in the other two dimensions. And then we have the issue of entanglement. If this particle is entangled with something else, then you're completely out of luck, because the other particle affects the spin of your particle, and it could be on the other side of the universe. And they don't know why, but they say that's the case. And of course that confirms the rope.
Yeah, obviously.
Yeah, because the rope can only spin one direction or the other. But they call it entanglement. They say we don't know how that happens because it's action at a distance, at a gazillions of years, light years distance. And so if the particle is entangled, you know even less about the spin because the other particle affects this one.
But aren't they all entangled?
Yeah, they're all entangled. And
entangled by what?
Yeah, I mean, they can't. I mean, how do you have entanglement in a particle world? And they say, well, we can't explain it. Of course, you'll never be able to explain it because entanglement requires an elongated mediator.
Yeah.
Period. There's no argument about that. And I mean, from physics point of view, from mathematics, from a mathematical point of view, you can do anything you want. You can put angels in there if you want, God, magic, whatever you want to, black magic, whatever you want to put in there, incantation, words of magic. What do you call those? Those charming words. Those what do you call it? Like abracadabra or whatever that magicians use.
Spell.
Yeah, the spell. You can throw a spell at it and it'll work. Mathematics, you don't have to explain how it works or why it works. All you have to do is put in an equation and say, it does work this way, and we described it mathematically. That's what they do. But, how do you explain entanglement when entanglement says that this particle here affects this one over here in any way? And not only in a gravitational pull, attractive kind of way, but also in the way this thing spins. That's entanglement. Entanglement says that if this one spins clockwise, when they measure over here, they find that this one spins exactly in the opposite direction, counterclockwise. So how do you make sense of that? Well, you can't make sense of that in quantum, in a particle world.
There's particles on the outside of the tube that make them do that.
So entanglement is a big headache. Tunneling is another issue because the particle reaches a point, but after that it continues as a wave. And so here you have the horse running along the tracks, and it beats the other horse. Why? Because it stretches his neck as a wave.
Wait, you're gonna what?
Yeah. Think of two horses running a race, right?
No, but like, what are they actually talking about?
They're talking about that the particle converts. In other words, they say, how did the particle go through a wall, tunnel through it? How did it go through something and end up on the other side? It's very easy. It turned into a wave, and the wave went through the tunnel.
Wait, but what are they talking about?
Like they accelerate a particle.
Light
No, they're trying to they accelerate a particle.
Okay.
And it's supposed to be here, but they find it over there. They find it at a different place, and they find it like it went through a wall. They say, how did this particle go through the wall? They say, very simple. Right at the moment it's going to hit the wall, like you're with your car, you turn into a wave and you're on the other side. Very simple. You turn into an angel, you turn into a spirit, just go through the wall, no problem. See, we fix everything in quantum mechanics. So there's no explanation. You can't look at the movie and say, oh, I understand the mechanism. Yeah. You can't do that with quantum. With quantum, you got to take a course in college, and what they'll show you is an equation and say, look, this describes what we observed.
They're basically saying the math says this, so it must be so.
Yeah. But we won't change the particle model.
By it must be so, they mean exactly that. Like, why is that how it works?
We don't care how it works.
Yeah.
We don't know how. No, they say we don't know how it works. It's a weird world.
How did the particle go through the wall? It just did. The math said it did.
Yeah, so here's the equation.
I don't know how it did. We're just gonna say it did.
Here's the equation.
Yeah.
That's how they do it, and so you'll never get you're never going to get a straight answer, a rational answer from a mathematician, because he's only going to do descriptions, he's going to do equations, and when you push him against the wall, he's going to say, well, first we don't do explanations, and second, that's what the equations say. That's what we observed in the lab, and here's the technology to prove it.
The universe works in mysterious ways.
Yeah, that's how all that works.
I mean, you could literally switch out everything a religious person says about God and just replace the word God with universe.
Yeah. Essentially, that's how
the universe has a plan for all of us.
Okay, so let's get to the subject at hand, finally. This was supposed to be the subject at the beginning of the week. It ends up being the subject at the end of the week in the last few moments. Okay, we begin very quickly with the standard model definition of particle physics is the theory describing 3 of the 4 known fundamental forces, okay? And so what is a force? A force is a force, of course, and here it is. It's the fundamental interactions, also known as fundamental forces, are the interactions that do not appear to be reducible to more basic interactions. There are 4 fundamental interactions, Okay, so these are simply an interaction. What is it? It's an interaction. Okay, so it means that 2 particles are interacting somehow. Okay, they're touching each other. They're having some kind of interaction, and they want to know, how a photon affects you, how a graviton affects you, how a gluon works within the subatomic world, how a weak force, the W forces, how they act in the subatomic world. Okay, and so what is an interaction? Okay, and so let's go with that. Here we have. It says each of the known fundamental interactions can be described mathematically as a field. So an interaction is a field. Listen to that, okay? The interaction suddenly becomes a field. What is a field? It's something that's dispersed. Bunch of particles apparently that occupy the field, but what they're looking at is a region, and they're saying something occurs within the field, within this region, and we'll call that something that occurs, we'll call that a field. We'll give it a noun. We'll turn it into a noun, we'll call it a field. Okay, so something that occurs in this region becomes a noun, something that you can now move around as a whole.
If it starts raining in Frankfurt, we're going to call the field around, the field of wetness around Frankfurt, that's just
puddle.
The rain field, essentially.
The rain field.
Everything here is
wet.
And
it's made out of raindrops.
Yeah.
So the field.
But we don't really care about what it's made of. We're only caring about everything within this vicinity is, strangely enough, wet.
Yeah, but it's important to know that they conceptualize it as raindrops. They'll say the field of rain is made of raindrops. At least that's what they conceptualize. So we can't lose track of that. And when you look at each drop, every raindrop, you say, well, what is a raindrop? Well, that's another field. It's a localized field.
Well, it technically is. If you zoom into the raindrop, you have a cluster of atoms.
Yeah.
But then you zoom into the cluster of one atom, and it's also a cluster of particles. You zoom into the particle, it's a cluster of
and when you have many of them, then you get the quasars, because at that point, when you have many of them, then you have this emergent property.
I didn't understand that at all.
Well, it means no. Think of it this way: 5 people, right? And this guy comes with a color red. The other guy comes with a color blue. The other one with a color green. Everybody comes with a color. They put them together, and they turn all of these colors into a color white. So white is an emergent property of each one of the components in the system. That's an emergent property.
Okay, but then
it's a contribution of each individual member to the system, and the system and a new property emerges from the system. In the case of particles, of quasars, Quasimodo, whatever. In the case of particles or quasi-particles, they're saying that you have different properties from different individuals or components, and a property emerges, and we're going to call this field property, this encompassing property. We're going to call it, what was it? Plasmon. Blue ball, blah, blah, blah.
No,
They
but
come up
that's
with all these
because-
names.
But then the question is, what are the quasi-particles made out of?
Yeah, and again, they don't care. They just describe them mathematically. They give them a name. They describe it mathematically with an equation, and they say, well, it's an emergent property of the system. And that's all they do. They just describe mathematically. Okay, so is there a difference between a field and a famous wave function? Because remember, all this has to do with Mr. Heisenberg and the fact that, with Schrodinger, who came up with the Schrodinger equation. And you know, he came up with this equation that essentially says, look, we can tell you the shape of the orbital, and the way you do this is you can figure out where the electron can be around the proton, its proton. So if you have an electron going around a proton, they can tell you more or less what the shape of the orbital is. The orbital is the region where you can find an electron. And that's what Schrodinger's equation does. It tells you where you can find it. It's the location, essentially, of an electron point particle. You have to treat it as a point particle, okay? Anyways, it says classical fields are sections over space-time, whereas wave functions are probability amplitudes over configuration space. Quantum fields are local operators over space-time acting on wave functionals over the space of classical field configurations. What are they talking about? They're saying, look, the famous wave function, it works at the quantum level, and the field, it's a field at the quantum level, whereas the classical field, which is more like what Einstein had there with his relativistic fields, that works on a cosmic scale. So what is the cosmic scale made out of? It's made out of a lot of small quantum fields. You aggregate them, and you got the whole rubber sheet.
We got fields on fields on fields on fields on fields on fields.
You got fields made of fields.
And what do we mean by fields? Clusters of balls made of clusters of balls made of clusters of balls.
Right, because people ask, what's the difference between a field and a wave function? And a wave function is a localized field. You can think of it as that. That's what it is.
What do you mean by
well, localized field is it's a field around an atom or a subatomic particle. Every particle has a field. Remember, these fields extend eternally. You have a muon field. You have a pion field. You have an electron field. All of these have fields. And then you have the field of charge, field of color, a flavor. You got all these fields, and you know, somehow they don't get in the way of each other because all these fields exist simultaneously. Why is that so? Because when the guy has to deal with flavor, you know, he says, okay, I'm just going to do fields of flavor today. And so he works on the field of flavor, say, okay, this works. But it's like they don't care that that field seems to interfere with the field of color, the charge, the gravitational field. You know, all these fields are superimposed upon each other, and they don't have a problem with that either because they do talk about superimposition. In quantum mechanics, you can have two particles superimposed.
Oh, we should have done that GIF. We still haven't done it yet.
About what?
The GIF about the superposition, where you were going to film the program that I had there.
Oh, okay,
Me putting all the balls in the same spot
we forgot
and blowing them out.
No, but I got something here anyways that's along those lines, and let's see if I can get it here. Where is it? Here. Oh, here it is. It starts here, and it goes something like this. You can see that an atom that they're showing there can have two states, two energy states. In one case it vibrates, and the other one it doesn't vibrate. And so they both occupy the same location. In other words, they're superimposed upon each other. One can be stimulated and vibrates. The other one, one is not vibrating, the other one is vibrating. And so you can have a superposition of states. Okay, if you can think about that. But that it doesn't stop there. It goes to the second part, which is this one. It says, you know, two particles can have the same location, essentially. they can occupy two positions at the same time, and they can also and two particles can occupy one position at the same time. So you got both situations. Two particles, one position, one particle, two positions. Okay? Two locations. So they have all these things. As you can see, this is no longer rational. It's got nothing to do with rationality, but they say, well, that's what we've seen, you know, in quantum. That's what we see in the lab. But is this what they saw? Or is this what they inferred and deduced? If they can't see the particle, obviously they're inferring these properties, and they say, well, how else can we explain it? The particle has got to be at two places at once. And you say, how can that possibly be? And let me show you
I like how you said, which is probably what they say, how else can you explain it?
Yeah.
Which is basically a failure of the imagination.
Yeah, essentially, it's the problem comes down to the fact that they want to explain everything with particles. That's where the problem is. Instead of saying, look, we got to abandon the particle hypothesis because we can't explain anything in the microscopic world.
Because there's a failure of the imagination. They say, how else could you explain this?
There's more than this. No, that's one part. Failure of imagination. Let me give you the other part. The other part is that you can't put, you know, an extended object in an equation. You can always put one value, and that one value is that particle, that wave function turned into one particle. So, you know, the particle represents one value. True. And they can deal with that because they say, oh, mathematics deals with one value. What are we going to call it? Let's call it a particle. So now the particle, which is a dot, which is the, you know, Euclid's point. You know, you don't put the point in there. No, you say, what is the point worth? What is the value of the point? Well, it's a pair. What is it?
Bond, covalent
no,
bond.
The mathematical pair. What is it called? The what's the word? Within parentheses, A and B, comma B. What is that? The ordered pair. An ordered pair is an XY location. You know, 2 feet to the left or to the right. Or right, in your case, to the left. 3 feet upwards, that's where the treasure chest is. That's an ordered pair. You can have an ordered triplet. If you have a z-axis, you can have more dimensions, right? More coordinates, and you can just keep getting more ordered, whatever, ordered, what is it, quadruplet, quintuplet, and so on, because those are the dimensions these people are talking about. That you just give another number, another number, another number. So what do? They need to put that number, even as a matrix, they put it into an equation. So the particle represents a point, the point represents a location, and location is a number. And so they can do that. But now imagine if I say, well, you know, the universe, the physics doesn't run with particle, it runs with a rope. Yeah. What are they going to do? Put a rope in an equation? Say, look, for this, we're just going to put a rope in there. What are they going to, you know, what sense does that make? None.
You can't even measure the rope because there's no beginning and end.
Yeah, in other words, it's got nothing to do with math. The rope has nothing to do with math, other than maybe the speed of...
It doesn't have nothing to do with math because there are equations that can describe the shape that you propose.
Frequency, wavelength.
But it's not as straightforward as particles, where you just have, okay, we have a dot here, it has X, Y, and Z, we're just going to give it that.
Yeah.
You can give it whatever properties you want. It's literally just a placeholder. That's what the particle is. It's just a placeholder to hold all your properties. But when you have a rope and you actually have to think, okay, wait, this thing has no beginning and end. We don't know how thick it is.
Yeah.
Right? We don't know how tight the ropes are wound, and it probably changes from atom.
All you can do is have speed,
There's
maybe
no way
wavelength.
to empirically measure a single thing about this. Almost.
Yeah, well, you can, the wave, the link length, as I call it, how long the link is, what the frequency is, how many links per unit measure.
Can you count the links?
Yeah, you easily, very easily, because
with God's eyes, or
no, you can calculate it, because you can say, look, what is the frequency, and the frequency is so much. You know, we do deal with frequency every day in a mathematical and mathematical physics world. They deal with frequency and wavelength. And if you say, what is the wavelength of this rope? In other words, what is the length? Well, the length is so much, and here we have this chunk of rope. You can calculate, you know, what the frequency is. How many goosebumps there are.
Not how many goosebumps.
Yes, you can. What do you mean?
Is that actually how many links there are?
Yeah.
Literally?
Yeah, you can calculate. I mean, you know, that's how they calculate frequency versus wavelength, because the speed of light is c is fixed, 300,000 kilometers per second. It's equal to frequency times wavelength. If you know the wavelength, the length, you can calculate the frequency, and these three numbers can be switched around. So yeah, you can calculate exactly how many links there are if you know the link length, and you can know the link length through you know, all these spectrometers. They you know, come up with how long the link is. In other words,
so
what
the
wavelength is.
I just looked up what infrared is.
Yeah,
Yeah,
like red is 620 nanometers, right? And so that tells you how long the link is. That's the length of the rope. And if you have
long
the link of, yeah, from beginning to end of one link,
700 nanometers.
620 nanometers.
That sounds too high. We're talking about a rope.
Yeah, we're talking about nanometers.
That's not, but that's not enough.
Hold it. That's it, right? Yeah, nanometers.
Nanometer.
Yeah, because you're talking about you know.
How much is a nanometer?
It's what is it? Nanometer is what was it? Micron. Say it's 9 zeros on of a meter. You know, put a meter, put 9 zeros in a number, and that's your nanometer. And then angstrom is 10 or it's been a while.
And that's enough, because you'd think the rope link is so small.
Yeah, but you're talking about a meter is, you know, a yard.
Yeah. And
you divide that into...
I guess now it's my failure, the imagination.
Yeah, you divide into millions of parts, more than a million. You're dividing into a billion parts.
Okay, but
and that gives you that gives you the link.
Can you still count the links though?
Well,
that tells you how big the link is.
How long
and then you measure.
You got waves this long, or you got radio waves this long.
But then you measure the distance and divide it by the distance, and that's how many links you got, right?
Well, you got 300,000 kilometers per second. You got that. That's the speed of light. That's a fixed value. It's a constant, and that's equal to.
But do you need that?
Yes, you do.
Because
we're talking about rope.
If you just need infrared, right? If you have an infrared beam from
and
here
you know the length of the link.
Yeah, you know the length of the.
And you got 300,000. You calculate the frequency.
300,000.
Yep, to calculate the frequency.
No, but assuming you already have the frequency, and you have the distance between the two objects.
That should between the link, the ends of the link.
Ends of the rope.
No, ends of the link.
You have a laser here, and it's shooting an infrared beam to a wall.
Yeah.
And you know the distance.
Yeah. From here to the wall. Yeah.
And you know exactly what the frequency is.
Yeah.
600, whatever.
Yeah.
Don't you just divide the distance by the frequency?
And that's but I think the frequency is the tough one. That's the tough one.
Well, what do you mean?
Yeah, because no, hold it. If you have the laser here and you're pointing against the wall, you know the distance from here to the wall.
Yeah.
You know that the speed of light. Listen to this. Speed of light 300,000 kilometers per second. You know that c, that little c, that 300,000 kilometers per second is equal to frequency times wavelength. Frequency times wavelength. That's the equation. And if you know that the wavelength is 620 nanometers, then all you have to do is just divide the light, the 300,000 divided by the wavelength, and that gives you the frequency.
So you can literally calculate how many links.
Of course, and frequency will tell you how many links you have. That's the way it's done. So you can calculate this, but my point here is that
you're rolling over that, but that's pretty crazy that we can count links on an invisible nano rope.
We can calculate it even though we can't see it. But that's what they do. They do that every day with when they deal with frequency and wavelength.
Well, what else can you calculate about the rope?
Well,
because we're basically going down the list of things you could calculate.
Not too many.
You can't.
It doesn't have weight because you know when you're pulling on the donkey, you feel the weight of the donkey, but you don't feel the weight of the rope on which you're pulling it.
That's
because it's in the wrong direction for weight.
But can't you just say it doesn't have weight?
Well, that's the point. It doesn't.
It's not calculatable.
But that's why they say that the little c, you know, a photon is massless, because they say we don't know why it's massless. It's massless because it's the rope that you're pulling on. You feel the donkey, not the rope.
I want to go more into the rope, but time.
Okay, we'll see you again on Sunday, same time, same station. And yeah, there are a couple more subjects to touch here on the standard model of
Forget the standard model. I want to talk about the rope.
We'll get to the rope.
Some year.
No, but we gotta we gotta make sure we understand what quantum has. Yeah. We gotta go through the boring stuff to get to the good stuff. We'll see you on Sunday. Bye.